Alright, we're going to redo the lecture on series. The term series refers to infinite sums. Now, the ancient Greeks did not believe you could add infinitely many positive numbers together and get anything other than infinity. But this simple example will convince you otherwise. Imagine that you had a pie and that you ate half the pie. And then you ate half of what remains. And then half of what remains. And so on and so on. In this way, you never run out of pie. So this sum has to be less than or equal to 1. Similarly, if you take a number between 0 and 1, you can think of this as a portion of the pie. And if a is very close to 1, it's almost a whole thing. So if you measure the pie clockwise, here a is a portion of the pie, it's almost the whole thing, so very close to the starting point. And by eating half of what remains, you eventually surpass a. So this has to be bigger than any number less than 1. So this sum has to be bigger than any number less than 1, so it has to be at least 1. But at the same time, it's at most 1, so it has to be 1. What do series look like? Series are infinite sums. We've already introduced notation for sums. If you think back to Riemann sums, we introduced the sigma notation. So series, let's take an example. This is an example of the notation in use. What does that refer to? The sigma notation, you'll recall, is the sum, right? So this is the sum of the terms when n is 1. This is 1 over 2 to the 1. Plus sigma notation when n is 2, 1 over 2 squared. Plus when n is 3, 1 over 2 cubed. And so on and so on. Or if you prefer, 1 half plus 1 over 4 plus 1 over 8. And we just argued that this series is 1. Let's take a few other examples just to get acquainted with the sigma notation. Consider the series 1 over n squared. Let's just write down the first few terms just to see what's going on here. When n is 1, this is 1 over 1 squared, or 1. Plus when n is 2, 1 over 2 squared, plus 1 over 3 squared, and so on and so on. Or if you prefer, 1 plus a quarter, plus 1 over 9. The next term would be 1 over 16, and 1 over 25, and so on and so on. Exactly. Let's consider one more. The series negative 1 to the n plus 1 over n. So when n is 1, this is negative 1 squared, which is 1 over 1. Still 1. Plus, when n is 2, we have negative 1 cubed, which is negative 1 over 2. Plus, when n is 3, Negative 1 to the 4 is positive 1 over 3, and so on and so on. The next term would be negative 1/4, and then plus 1 over 5, and so on and so on. Can we describe what a series looks like? Right? What are we doing? We are adding some terms. A series has the form the sum of an. This is what a series looks like. And you see the issue. Right? Because before introducing series, we were looking at sequences. And sequences look very similar. And there's an obvious relationship between the two. In a series, you are adding the terms of a sequence. And if you're unfamiliar with the two objects, it's very easy to get the two confused. That's why you have to master sequences before you move on to series. But assuming that that's done, we want to be careful, right? Because they kind of look like the same thing. But these are two very different objects. Again, the obvious relationship between the two is that in a series you are adding the terms of a sequence, but there's a more important relationship, a more fundamental one, and it's this. From a series, we're going to build a sequence known as the sequence of partial sums. So from a series, AN, we build a sequence known as the sequence of partial sums. And let's illustrate how that's done. We define S1 to be the first term. S2 is the sum of the first two terms. S3 is the sum of the first three terms, and so on and so on. Sn is the sum of the first n terms. And we follow that up by saying that a series converges if and only if the sequence of partial sums converges. And in this case, if the sequence of partial sums converges, we say the series converges and they converge to the same thing. Let's illustrate with the first example we saw. If our argument did not convince you, right? Remember that pie argument where you're eating half of what remains? Let's repeat with that series. Let's calculate the sequence of partial sums. S1 is the first term. S2 is the sum of the first two terms. And S3 is the sum of the first three terms. And so on and so on. Sn is the sum of the first n terms. Now, as it stands, there isn't much to do with that. However, there is a nice closed form for Sn. We can get a nice closed form via a trick we've been using over and over again, namely multiply by 1. Let's rewrite Sn here. Here is our Sn. Let's multiply Sn by 1. Let's multiply Sn by 1 minus 1/2 over itself. You're multiplying by something over itself. You're multiplying by 1, you're not changing anything. What does that do? Let's multiply, well, first of all, we'll leave the denominator as is. And let's multiply everything by 1. So 1 times this, 1 and so on, right? So you get a 1/2 squared, all the way to 1 over 2 to the n plus 1. And then let's multiply everything by 1/2, subtracting the whole thing. So minus 1/2 squared, minus 1/2 cubed. Oops, sorry, I said n plus 1, but it's really just n, right? 1 times 2 to the n is 2 to the n, is 1 over 2 to the n. And then if we multiply by 1/2, 1/2 squared, 1/2 cubed, all the way, this is where the 1 over 2 to the n plus 1 comes in. And if we ask ourselves, what was the term before this? Of course, the term before that was 1 over 2 to the n. So why don't we say this, minus 1 over 2 to the n, minus 1 over 2 to the n plus 1. And now observe what happens. We have 1 over 2 squared minus 1 over 2 squared. These things cancel out. The next term would have been 1 over 2 cubed, which cancels with this minus 1 over 2 cubed. Everything cancels in between, and 1 over 2 to the n minus 1 over 2 to the n, this cancels out as well, leaving you with 1/2 minus 1 over 2 to the